running just what we did yesterday before my colleagues comes in. So I just want to make sure that we start. So the first thing I would like to try to emphasize is that when you are doing your analysis, it is advisable that every analysis that you do, you create a folder, and in that folder, you will have the data set that you're going to analyze. You'll have the scripts, and then you'll also have different results, and anything that is associated with that project should be in that one particular folder. This is going to make it a lot easier for you to follow up with what you're doing on your computer. But for R also, this is also going to make it easy for you to be able to get the files that you're interested in. So we looked at yesterday how we set up a working directory. So the folder that we shared that we're working on yesterday, mine is labeled here day 2. So if we open day 2, you can see in this case that I have the script end with .r. So what I have as data2 script is my script, and then I also have the data set in my in the same folder. So what I'm going to do, I'm just going to open this. I can just right click and I say open with R, which is the default, R Studio, which is the default. So I can stop sharing the other screen so that I can share. I share my R Studio now. Okay. So from here, now we started with our showing our 4 different windows. I know there are people who are struggling a little bit with some of the windows disappearing. So here, for example, I have, so here I have my 2 windows on this side seems to be collapsing on each other. So you can see we have this that can expand, we have this that can reduce the size. So you do this, it will disappear. You can do this, then you have both of them coming in. So, but you can always try to adjust this, depending on what you want to show. So we started with the installing the packages. So those who already installed the packages yesterday, you don't need to do anything. So now for me, because I've already installed them, so I just want to make sure that they cannot be used. So I can put this one here. Once I put this, then the program cannot run. Okay. So you need to have the packages in. We did the installation yesterday. So the first one installed for us the EMINs. The second one installed for us our tidyverse, which is used a lot in data manipulation. And then we also installed Agricole, which is one of the main package for doing data analysis. And then we also installed our ggplot 2. After doing the installation, you cannot use the packages unless you call them using the library. So the first thing that we need to do, we need to be able to run this line number 5, 6, 7, 8, and 9. So we can, for you to run this, you can just put a cursor anywhere on the line.
Your phone has been ringing.
This is not me.
And then you can have that. So we can run line 6.
Yes.
So if you run line 6, you can always see, sometimes you see red, but if it is not an error, that is okay. This one is welcoming you. That welcome to E means caution, you lose important information if you filter this package results. See that, okay? We can also do tidyverse. Once you do tidyverse, it kind of gives you some information that attaching core tidyverse packages, and then it also tells you that, okay, you have deployer, you have forecast, you have Gg2, you have all this. So some of this also comes together.
That's for which phone?
Then we can also run.
Is it iPhone?
Run. Yes, Atur. We are hearing what you're saying.
Oh, sorry.
That's fine. Okay. So we can also run line number 8, which is to call the Package Agricole, and then we run line number 9, which is to call the package ggplot. So once you have this, that means you have the tools ready for you to do the analysis. I see some people started raising their hands very early today. I don't know what is going on. If you have any question, please put it in the Q&A, so that we're able to have that. Festus Otieno, you're raising your hand. Is there anything you want to say? Can you type in the Q&A? The link will be reshared, and my colleagues are there to answer any questions. So put your comment or what in the Q&A section, and then we'll be able to get to you. Okay. So that is the first thing is make sure that the packages are there, and then make sure that you call the packages before you can do the analysis. The next thing that we want to do is we are going to call, this is our data set. Now we are going to call this data set, but before we can call this data set, we need to create a working directory. So I talked about a working directory as a folder in which you have everything that you need to run R. So you have your data in there, you have your R script. So before you can start the analysis, you need to make sure that you are in the right working directory. You can see mine from here. It tells me that I am actually already in the folder. I went to document trainings to forum September 2025 and day 2. That means I'm already in that folder. But yesterday we showed you how to do that. So the first thing is you need to look for on top of the RStudio, on top of your computer, you need to look for where it's written session. So if you click on where it is written session, you choose set working directory, and then you choose a directory. So the first thing is you start with session. You go to set working directory, and then you go to choose a directory. Let me try to type it here just for you to see. So you say session. That is what I was talking about, the word session. After session, you go to set working directory. And then you go to choose a directory. That is but you need to look up on top where the session is. Okay, so I can go up here and I go to sessions, I set working directory, I choose a directory. Okay, so once I've chosen, once that the box comes out, I go to look for where my folder is. I go to my document. Under my documents, mine is under trainings. So I need to look for where my training is here. Under training, I go to the forum, and immediately the file that I want, the folder that I want is day 2. I don't need to go inside this folder. I just click on this folder, and then I go down where it is written open. I click on that, and then I'll find myself in that working directory. Now, how do I know whether I'm in the right working directory? You can read on top here, but you can also check. Let's say on this side, you have these files. So if you click on the files here, you should be able to see that you have some of this. These are the files that are in the working directory. So you can see here that I have data2 script.r. I have model for different experiment. I have overview of statistical model. Then I have the RCPD with covariate .csv. So that is what you do. So we have set our working directory ready. Okay, so we can go to this line here. Those who are here yesterday, or at least those who already know a little bit of R, the file that we have that we want to read, this is the name of the file, and you can see that is present in our folder, in our working directory. So we use this read.csv. Read.csv. The name of the file should be in a double quote. Okay. So once we run this, it should already show me here that in the environment that I have what I've called DF. It has 20 observations, and it has 4 variables. That is what we have here. Then yesterday we started looking at things like what are the names of the columns.
Dr. So Thomas.
Yes, please.
Calvin has a question in the Q&A. Maybe you can look at it briefly.
Okay. Yes, I've set a working directory, and I have the work, but everything I try to recall, the data set cannot accept. I don't know what is wrong. Can you allow Kelvin to share the screen? Yes, Arturo, can you allow Kelvin to share the screen so that we can see what is going on? Yes. So Enoch saying that does opening a file in the folder automatically set the working directory? Yes, you can do that. You saw what I did. So please make sure you are in the right working directory. If you're already in there, then you don't need to worry about that. So can this gentleman be allowed to share so that we can see what is going on? Is Atu? Okay, as we wait for Fernando, are you with us? Okay, at some point we'll get you to know. But he needs to first check whether he's in the right folder or not. I guess probably he went inside inside the day2 folder, and that is where the problem possibly is. Okay, how many people are in the, can I see those who are in the right folder now? Okay. Okay, good. Can I see those who are not in the folder type 2? If you're not in the folder type 2. Yes, so Calvin is not in the folder. Hillary. Yeah, we need somebody to share so that we are able to see what is going on. Prof. Susan, can you get somebody to call her through to come and try to help? I don't know. It seems to be off his computer.
Okay, let me do so.
Okay, thank you. Kelvin, can you copy the error that you see and put it in the chat or in the Q&A? Okay, we can continue.
He will be with us soon.
Sorry, my internet went off. Let me reshare my screen again. Okay, so the head will give us the first 6 observation, and then line 19 will give us the structure of the data. You need to pay attention to any of the command that you run and the output. So this and what is in green is an explanation for what the command does. So under this one tells us that this is our data set. It has 20 observations and 4 variables. Selma, you're welcome. We want to see or let Calvin pass the screen.
You want to have someone allowed to share the screen?
Yes, or let Calvin.
Calvin. Okay, let me just quickly do that. Can the person raise their hand? I'm not seeing the hand. Please raise your hand up if you want to share the screen.
Yes.
Great, I can see you now.
Okay. Yeah. Well, let me stop sharing and then.
Okay, that's oh.
Yes, Calvin, can you please accept so that we move quick?
I'm trying to no, I have not yet given him a prompt. Can you check if you are the host? I'm trying to check who is the host so that we are able to get the right.
Yes, Calvin, you're certainly not in the correct folder.
Dr. Odong, you can also promote me to be a co-host.
Hey.
Atu is a host. He's not on the table.
Oh, let me try and see. I'm trying to promote you, but I'm not succeeding. I don't see. Okay, you're now the course, so I think that's fine.
Kelvin, I've promoted you to panelist. Thank you, Doc. I'm now a co-host. So Kelvin, please accept. Okay, you are in. You can now share the screen.
Calvin, can you?
Yes, can you hear me, Doctor?
Yes, we can hear you, but we want you to share your screen.
Yes, I'm trying to share my screen.
Okay.
Are you able to see my screen?
Yes, okay. Okay. Okay, so where can you go to sessions up there?
Okay.
Okay. Choose a directory. Where is it on desktop?
Yes.
Okay. Click on that. Is that is where the data is? No, don't open it. Go back.
Yes.
You open with the word down. Okay.
Yes.
So can you run now?
I have it done. This is what it's
First,
doing.
go down.
This is it, Doctor.
No. First clean up clean up your R console. Okay. Can you enter in that? Just type the enter key. Tap on the enter button of your computer. Okay. Now try to click on the files on the other side. On your left-hand side, the word file. No, on the left-hand side, on the lower quarters. No, go on the left. Not that one. There's another file where there's a plot. Do you see where you get the plot under the environment, below the environment?
Oh, I see.
Do you see a plot there? Can you click on that? But now you see the name of your file is as a 2 in bracket.
Yes, I see.
Do you see that is where the problem is? So you first need to go and change that name there. Maybe you put a 2 in bracket to that. That's, you're trying to call a file that is not there. So you try to modify the name of the file.
I get now where the problem is.
Yes, so what you can do is you can put a 2 on your line number 14. Go to line number 14 and put a 2 in the bracket, not in the there in front there. Put a bracket there. That 2 should be in a bracket. Try to run that line. Okay, just go and modify the name of the folder. The name of the file, then you should be okay.
All right, let me try that.
Okay. You can stop sharing now. Okay. So you can see that's the bit of the challenge that you need to address. Okay, let's run this rather quickly. So we have the, okay, so from the structure, we see that the block is an integer, treatment is an integer, but then you have the initial biomass, which is an integer. We have yield, which is an integer. But yesterday we said this 2 needs to be converted into factors. So the next 2 line 21, mine line 21 there, line 22. So in line 21, we are converting block into a factor. We are converting treatment into a factor. So if we check now, we run line number 23, you can see now that the first 2 are now factors. Okay. So with the first 2 now being factors, we are now ready to start doing our analysis. So I think this is clear to everyone. Okay, so I'm not going to run these ones here anymore. You can run them. What I want us to do is I want us to go up to, let's go up to line number 88. What I have here as line number 88. Okay. We have a lot of things to cover, so we need to be able to move in a certain speed. So yesterday we looked at, so we are trying to fit 2 models here. We are fitting a model for yield being explained by treatment and block. And we say this is when we have not included the covariate in our model. Then in the second model, we are fitting yield. This time we have treatment, we have block, and then we also have the covariate, which is our initial biomass. So we're going to run these 2 commands. Okay. So you can see from here that we've created mode 0, which is a list of 13. We have created mode 1, which is a list of 13. So these are the 2 models that we have created. Now we can start looking at those models, the model that we have created. We need now to start looking at them and see exactly what is going on here. Okay. So the summary here is going to give us all the parameters of the model that we have. So if you run for line number 92, so you can see from here, let me first try to expand this a little bit. So you can see from here that it starts by giving you the model that you've run. It gives you the residual, the minimum residual, the maximum residual, and then it gives you the other one. Now, when we come to the model here, now we get our intercept, we get the effect of treatment B, we get the effect of treatment C, we get the effect of treatment D, then we get the effect of the blocks, the different blocks. So as you see from here, the treatment A and the block 1 are not there. So that means their information is contained into the intercept. And then you can also see from here that the intercept has 3 stars. So 3 stars, according to this, mean it is significant at 0.001. And then the treatment B has a dot. That means treatment B is different at 10%. Now, then you look at, there's another one, block number 4. It has a dot, which means it's at 10%. Now, this test here means you're testing for the treatment, you're comparing each treatment with treatment A. For the block, you're comparing each block with block 1, because those are the ones that are set as the baseline. So you can see from here that when we run a model without the covariate, only the intercept is significant at 5%. Now, if we go and check our model number 2, which is the model with the covariate in, okay? So the first thing here, it tells us the different, and this is the model that we have got. We have treatment, we have block, we have initial biomass. Then, okay, so here we can see now that we have the intercept. So this is the estimate. This is the last line is the probability. So we can see that the intercept is significant at 0.001 alpha. We find treatment B is now significant. Treatment C is significant. Treatment D is significant. So we can see that all the treatments are now, the treatment B, C, and D are now significantly different from treatment A. Now, when you look at the block also, you find block 3, block 4, block 5 are also significant. And then we find that now we have another line for the initial biomass, which is also significant. So you can see that by changing the model from this to this, we're already seeing a big change in the level of significance of the different parameters in our model. So remember on day 1, we talked about the importance of specifying the right model and not leaving out any parameter that would otherwise supposed to be in the model. Okay. From each of these models also, we can get analysis of variance table. Let me check, there are some questions. So can you, Stephen, can you paste the error that you've got in the chat so that my colleagues can look at it and then tell you what could be? So what is the implication of the intercept? The intercept here is we are testing whether whether the intercept is equal to 0 or not. And remember, when we are going to come up with a model, this is going to help us because here we are looking at treatment A. So if treatment A is part of the intercept, so literally with the intercept testing, we are testing whether treatment A is actually equal to 0, the mean of treatment A or the effect of treatment A is equal to 0 or not. The difference between R adjusted and R is that R adjusted takes care of the fact that in a model you have you'll have more than you have more than one, is the difference in that when you have several parameters in the model, R adjusted would adjust for the fact that you have several parameters in the model. Okay, so if we look at the, let's look at what Stephen Odiambo has put in the chat, in the Q&A. So when you look at the model, you say block. So data must be a data frame, but do you have a data? I mean, the thing is that, Steve, did you run all the other lines, the calling, did you call the data? Can you promote Stephen can you promote Stephen to share the screen?
Okay.
Yeah.
Stephen, please keep your hand up. Okay, you can now move in. Stephen, you can now share your screen. Doctor,
Okay.
can you see?
Okay, sorry. Yeah.
Okay.
So now, okay, now what we want to see is that now Stephen, did you run the line? Can you go and run for us line number 13? Number 14, yours is number 14. Yeah, but but the thing is, you don't have the data. No. First go and set a working directory. Can you go to session up there? Click on this set working directory. Choose a directory. Click on choose. So where is the folder? Is there another folder inside there? No. Is there another folder inside that training folder? Can you open that? Double click on that. But there seems to be nothing inside that folder. No, please, if you did not run those lines and you did not see the data, there's no way you're going to run the line number 88 and gives you anything. So where is your data?
Steve, can you please unmute and respond to the question?
Unmute and tell us, where is your data? Where did you save the data that we are supposed to analyze?
I downloaded it directly from the file.
Yes.
And then let me here. Then I downloaded the data R directly.
So if you go to the file where you save the data, can you go physical that file and find out whether the RCPD data set is in?
Here it is. I've downloaded it 3 times.
Okay.
So
can you try to?
What happened there? When I downloaded it and then I right-clicked and it directed me straight to the RStudio. Then I just
No. We want to know where the data set is.
The data set is at downloads. So let me show you this one. Here they are.
So
can you
see let's
see
the folder itself.
There's R history.
You have only R history.
Yes.
Is there any folder inside there?
Let me open it again. It gives you an option of opening with the RStudio.
No. You see the name. There is. You go to your line number 14. Okay.
Okay.
Do you see in the bracket you have RCBD with covariate.csv? You see that line number 14?
Yeah.
Now you need that data set there. You need to find out where it is.
Okay.
Thomas, let him download the materials from the Google Drive and then put everything within the R training folder. That's when he will be able to have the commands run.
Yeah.
Oh, I've realized where I messed up. I only downloaded the one item, not all of them.
No, you need all of them because then you are supposed. Okay, the whole idea here is that why we indicated that you need to make the folder working directory because you need to look. This data set need to be in that folder so that you're able to actually run that number 14 successfully. Otherwise, then it will not work. It's like you're trying to pick something from you're trying to pick maybe a suitcase from a room which doesn't have that particular suitcase. So you need to have the suitcase in the room before you can open it or carry it away. Okay?
Okay, thank you.
Yeah, so you can stop sharing. You go and download everything and then you can follow. Okay, you can stop sharing.
Thank you.
Okay. So Judith, you're saying model 1 is not found, but did you run model 1? Because you need to first create it before you can run it. Okay, so let me go back. Okay. So before you can go to line 88, you need to run all these lines here. You need to run from line number 13 up to line number 23 before you can go to line number 88. Okay. Judith, before you can run this line here, you need to have run line number 81. So if it tells you that something is not found, that means the object has not been created. Okay. Okay, so we looked at the summaries for the two, and then we can also look at the analysis of variance table. So you can see from here that this is how a typical analysis of variance table for randomized complete block look like. We have treatment as a source of variation with 3 degrees of freedom. This is the sums of squares. This is the mean sums of squares. This is the value, the F value, and this is the probability. So you can see from here, this is for treatment. So there are 4 treatments. They have 3 degrees of freedom. So you can see from here, this is our block. And we seem to see that there is some significant differences between the blocks, but there is no significant differences between the treatment if you run your model number 1. Now, if you look for, that is mode 0. If you look at mode 1, so mode 1, you can see now that after we included the initial biomass in our model, now both the treatment effects is now significant, the block effects now significant. So by taking into consideration, or first of all, adjusting for the initial biomass, we are able to have a better test for our treatment. We are able to compare our treatment and we got a good results. Okay. So somebody said that block did not appear on my coefficient. That means you did not run a model with that. So the next thing that we are going to do is yesterday we also ran we just estimated the mean. So we can run the mean for model 1, we run the mean for model 2, and then we can compare them. So we did this yesterday. And then, so these are the mean for A according to model 1 is that. According to model 2 is that. Model 1 for B, for C, and for D. Of course, it gives you the standard error. It gives you the degrees of freedom. It gives you all this information here. So what we're comparing here is the mean for A with the model without the covariate. This is the mean with model with covariate. This is for B without covariate. This is B with covariate. So you can see there's a big difference between the two. See, you move from 39.9, almost 40, to 36. So there's a difference of almost 4 between the values there. Okay. So what am I trying to do here? I'm trying to show you that they actually, if you don't pick the right model, the analysis that you're going to end up with is going to have a bit of challenges. And then what we also did yesterday was to do what we call, to compare the pairs. So remember here, you can compare A and B, A and C, A and D, and then that. So let's compare comparison when you're using model number 1. Okay, so you can see that if you compare A and B, the difference between A and B is negative 6.7. And then the p-value here is 0.185. So that means A and B are not significantly different from each other at 5% significance level. Then A and C are also not significant. A and D are not significant. B and C are not significant. B and D are not significant. And C and D are not significant. That is if you use model number 1. Now, if you use the second model, which is our mode 0, mode 1, sorry. The first one is for mode 0, and this is for mode 1. So now if you change the model, of course, A and B are still not significant, but A and C are now significant. A and D are not significant, but B and C are significant, and then C and D are also significant. So here you can see that the results is average over the blocks. So the p-value adjusted for comparing the family of 4 estimates. Let me check if there's any question that I need to address, but I think my colleagues should be able to answer the other. So when you do analysis of variance, like if you look at these results here, now these results here will tell you that at least a pair of treatments are significantly different, but it doesn't tell you which pairs are significantly different. So that is where after that, then we go and make pairwise comparison. That is what we call a post-hoc test. So post-hoc test is now the test that you go and perform after you've done the analysis of variance and indicated for you that the results are significant. There are several tests that you can do. One of them is you can do Tukey's test, but the most common one that I use is what we call the LSD. So the LSD is also used a lot more frequently. So we can also make comparison using the LSD and then see the result compared to what we have up here. So the first test is we're going to look at the one for model 0. That is, remember, that's our model without the covariate. Then we can look for the one for model 1, which is the one with the covariate. So what I want us to do now, I want us to show the results of the 2. You're going to see from the result here. So you can see here now that in both cases, treatment B has the highest yield, followed by treatment D, then treatment A, and then treatment C. So this is for the model number, our first model. And then for our second model, I think there's something that I have not done right here. Okay, let me just do something different, I think. Okay, so this is our estimate for model 1. So based on this, what we're saying here is that the mean that share the same letter are not significantly different from each other. So you can see that B has letter A, D has letter A, and then A also has letter A. So what we're saying in this case is that based on the first model, there is no difference between B and D. There is no difference between B and A. But there is difference between A and C. You see, A and C don't share any letter in common. This one has A, and then this one has B. That is what we have there. So let me check the second one, I'm sure. Okay. Okay, so this one did not adjust the mean. I think I got it did not adjust the mean. So what it did, it just did the testing based on the value. So you can see from here that you have A. So B and D don't share any letter in common. So we're saying B and D are significantly different. And then C and A are not significantly different. But D is significantly different from A and C. Let me check if there's some question. Okay. Okay, so that probably we are going to talk about this again maybe tomorrow, or my colleague will say something about it when she comes in. The other thing is, okay, we have two participants with their hands raised up.
Thomas.
Yes, please.
Somebody says that he needs a repeat of module 88. I think that's line 88.
No, I think that is Stephen, because the one who did not have the data.
Oh, okay.
Yeah,
Okay.
because now the thing is, once the data is there, then the thing should run without any problem.
Okay. Thank you.
So there, I don't know, can you promote one of the people with the well raised hand up? And we see what if they can ask questions. So
I've promoted all of them.
okay, he said. So can you ask your question or? So somebody wants me to repeat the interpretation for the pairwise. The pairwise here is what we are trying to do is that we want to compare the means and see which means are significantly different from each other. So you can see from here, we have A and B. That means you're comparing the mean of A with the mean of B. And the difference between A and B accordingly is supposed to be negative 1.866. And this value here, if you test that using the two-case pair, you get a probability of 0.10, which means if our significance level is 5%, that means these two pairs are not significantly different. But when you come to this pair, you can see that our probability here is 0.04, which is less than 0.05. So in that case, we are going to care that A and C are significantly different from each other. When you look at A and D, you find that they are not significant.
Dr. Thomas is
sorry, somebody called my phone. I'm using my phone for the internet, so it went off. Yeah, but you've been promoted. What is the name? Dubusi. Can you ask your questions? Unmute yourself and ask question or share your.
Thank you very much. I don't have any question.
You don't have a question?
I can't notice raising my hand.
Oh, sorry. I think then you raised your hand accidentally.
Yes.
Okay, that's fine.
Okay. Thank you very much.
Okay.
Yeah, but we have another one. I think this is Abel. Let me allow him to talk.
Okay.
Yes. Abel, go ahead. with your question? Please go ahead with your question.
Please ask your question or unmute yourself.
Let us try to promote Mohammed.
Yeah.
Mohammed, please unmute and ask your question.
Unmute and ask your question, unless if you raise your hand accidentally, then we can proceed.
Hello, doctor. Thank you.
Yes, Rawia.
I am asking when using LSD or Toki or using together or just using one.
No, you only use one. I'm just trying to show the different things here.
Okay. Thank you so much.
Okay, you're welcome.
So, Doctor, can I allow another one? Or
yes.
Oh, please. Alphonse, please unmute and ask your question. Alphonse? Milogo, please ask your question. Unmute.
So if there are no questions, we can proceed.
Please.
Okay. So for now, what we're trying to do here is for this is just the comparison. Just I want us to look at, the line. This one is just to try to do some data visualization. It is a bit if you're using R for the first time. I know that the commands may look a little bit terrifying, but with time you're going to get used to that. Now let's first run the line, then I will try to explain what this line is all about, how it is working. So you can see from here, the first thing that we did is, remember we created this mean here. You see, this is what we have here. It tells us that the mean for A, for B, for C, and it gives you the lower confidence interval, the upper confidence interval. So what we are trying to do here is we are trying to convert this into a data frame. And we are creating a new object. After that, then we are going to use the ggplot like what we did yesterday. So this then becomes our data set. You want treatment to be on the x-axis, and you want the mean to be on the y-axis, and then you want plot points, and then on the point you want to add the error bar, and then you want to level. So we can run this. My line is disturbing me, sorry. Okay. So what I want you to note here is that I want you to note the confidence interval here. Not the confidence interval, the error margin, or because what if we don't bring in the first model, we did not put in our covariate. So that means the things that the covariate are supposed to explain partly becomes part of the residual. So in the second model, where we brought in the covariate, we should be able to have a smaller a smaller error bars, because we're supposed to have higher precision. So you can see from here that we have the means are different. The precisions are also different. This is the precisions here. The bars are shorter. That means they're more precise compared to the previous one, which had a longer value. And then finally, I'm going to do some checking for the model. Remember, we talked about checking the model. So what we want to do is we want to compare the residual plots. So here, what we can do, we can just use the word plot. Then you bring in the model that you created above. What the plot does here is that the plot is going to look for the different residual plots and present them to you, and you're supposed to look at them and interpret them in relations to the error, to the assumptions of analysis of variance that we talked about on the first day. So the first thing that I want us to do is I want to explain this bit of this command here. So this command here is going to allow us to create 4 different graphs. So here we're going to have 2 rows and 2 columns of graphs. So this command here will just just give us, just break up where we're going to have the graph into 4 different sections, and 1 graph will be plotted per section. So if we run this line 135, and then we run the plot, then you can see now we have 4 different graphs. Okay, so the first one is we have residual versus fitted value. So the residual versus fitted value is supposed to show us whether the variance is constant or whether there is no pattern in the data. So what we want to see here is we want to see kind of a random pattern. Remember, one of the assumptions is that the error terms are supposed to be independent of each other and they're supposed to be random. So this is supposed to talk about the randomness. This is what we call a QQ plot. So a QQ plot is supposed to test for independent, for a normal distribution. This is the scale plot is also supposed to test for whether the variance are constant or not. And then this is the leverage plot is supposed to tell us whether there's influential observations or not. But I'm not going to spend much time on this. I just want to run the second one. So you can see that the 2 models that we had different residual plots, and you can check these residual plots to be able to determine whether your assumptions are violated or let me check whether there's some few questions I can answer, then we proceed and I hand over to my colleagues in the next few minutes. Marwa said, what is the case if I have different number of replicates for different children? Could I run the same test? There are different alternatives that you can run. I say, can you explain the MEMD one? Let me check. So what I'm trying to do here with this is, remember, this is the means that we got earlier on. This is what we have here. Now, what we're trying to do is that we are trying to create another object, which is a data frame. So what we pick this result here, we make it to become a data frame. Because remember, for you to use a ggplot, you need a data frame here. So that's why what we're doing here, we are just creating a data frame that we put here, and that's the one that we're going to plot. So Ele Abebe, he said you have a plot that the figure margins are too large. The figure margins are large. What the solution for that is to try to adjust. Try to make this as large, or as try to play around with this. You can pull it this way, you can pull it up. Okay, that should be able to solve that problem. Check another one. The same for Judith, you can do the same. Now, Kibandi, I'm not sure what your error is. So what practice is required, which practice is required for one to master the outcome with? You don't need to, what you need now is you need to first know the basics of R. The basics of R that you need is that the first thing is you need to be able to to get your data into R, and you need to be able to know a few of these commands. You can always get a command from somebody, and you can modify that command in order to run with your data. Okay. Luanga is asking that, could you please briefly talk about the interpretation of the residual plot with reference to normality of the data? So what we have here, we have the residual plot here, the QQ plot. Now the QQ plot, for a normal distribution, the QQ plot need to be at 45 degrees from here. So if you have a straight line at 45 degrees, then you know there's a normal distribution. Otherwise, if you could have a tail on this side, or you could have a tail on that side. So for this data set, this is fairly normally distributed. The challenge here, you want to have some kind of randomness. Randomness in the sense that you don't have any pattern, but the red line here seems to indicate that there seems to be some kind of a pattern within here. But as you can see that the value of the residue here is small, from negative 1.5 to positive 1.5. So if it was on a wider scale, probably this would appear more like a straight line. So let me try to make something that will look a lot better here. Now, what I want to do is then we want to see whether the residue, we want to plot the residue for each treatment and see whether there is actually some differences. So let me first plot these residues, and then, okay. So let me try to stop sharing. Then I can share a graph instead. Okay, just hold on a bit. Okay, I think probably what you can see from here. So you can see from here that if we look at the residue for A, you can see that the residue for A, most of the values are centered around 0 is the one in the middle here. So you can see that A, most of the values are very close to 0, but we seem to have a problem with C. There's more variation in C and B, but less variation in the error of A and D. If you look at the block, we seem to be having a good relation, some kind of a good relationship between, so here you can see all the residuals seems to be similar in pattern. So in this case, you can easily assume that there is no, the correlation, you can assume that the residuals behave similarly in the different block. Now, what is more worrying in this particular case is that if you look at the plot of the initial biomass versus our residue, you can see that we seem to see a very strong relationship here, that if the initial biomass is low, the residue is also low. As the initial biomass increases, the residue also increases. Why is this happening? Because in this particular model here, model number 1, we did not include our covariate in the model. And what the residual plot is telling us is that there seems to be a very strong pattern still remaining in the residue. And that strong pattern in the residue, we need to be able to, what we need to do is we need to be able to correct it by including the initial biomass in our model. So if you calculate the correlation, so you can see from here, if you calculate the correlation between the initial biomass and the residue, you can see you have a correlation of 0.73. So that means there's a very strong relationship between the biomass and the residue. You can also do the same for the yield and the residue for that model. And you calculate the cost. So you see there's a strong correlation for the first model. But if you go to the second model and you run the correlation between, if you go to line 158, you run the correlation between the initial mass and the residue for model 2, you actually see, when you run the correlation, you see the correlation is very small. It's negative 4.7 times 10 to the power negative 17. So that means the correlation, yes, 0.00000 something. If you plot the residue, you can actually see that there's no pattern compared to if you look at the one for, let me compare with the one for, okay. So you can see that for model 1, for model number 2, where we have the initial biomass, there is actually no relationship between, there's no pattern in the error. When you plot the actual yield with the residue, you don't see any pattern. But in the case of model 1, you can see that there's a strong relationship between yield and residue. So that means that this model needs to be corrected. The ideal case is that you need to have your residue that is completely without any pattern. Let me answer a few questions, and I hand over to my colleague. Okay, I think there are no new questions here. Let me check in the chat. So I think now let me first hand over to my colleague so that she can pick up and continue from there. I know we can talk and talk and talk. So let me stop sharing and hand over to my colleagues, Susan.
Thank you, Dr. Thomas. Thank you, participants, for attending and being patient with him. Do you want a break now or we continue? Would you want a break now or we continue? Do you hear me?
Yes, we are hearing you loud and clear.
Okay, let me see. I said break, please. Break. Okay, let's have a break of 10 minutes. That means we'll start at 3:40 p.m. So let's go for a break and then we start at 3:40 p.m. Okay.
Somebody's saying, how do we save? Maybe you can demonstrate how somebody can save the graphs. I didn't do that.
Okay, I'll do that.
How are you, Ellen?
I'm well. How
You're
about
well. I didn't greet you.
I'm okay. Thanks for the presentation.
Thank you too.
You're speaking with low energy.
No. I'm okay. I'm following everything.
Do you need glucose?
Not really.
Just joking.
Dembure, how did you fail to run a single line today?
Oh, somebody has a question?
I think he's saying, Dembure, can you raise your hand up so that they pick you and you show us your screen for this break as we wait for. Promote him so that he can share his screen and we see why he failed. Because that was one of my former students. I don't want him to get away from here without getting anything.
Yes, Doc, I was getting.
Unmute.
Thank you. I was getting errors as I tried to run the commands from the beginning.
You show us your screen. Can you share your screen?
Okay, let me see. Now, how do I? I'm trying to find out how to share my screen
You see
here.
down, there's something in green written share screen.
Let me maximize my screen.
Down at the bottom.
Okay, yes.
At the bottom of the Zoom.
Yes, I saw it. Right, can you see my screen?
Why you not see your slides?
Can you see my screen, Doc?
Yes.
Yes.
Yes, so here I am. So this is my file here, line 12. This is where the script is, the folder with the materials. So as I tried to run line 14, it gave me errors throughout.
Line what? 14?
14, yes.
But you look at where is your. I don't see any file. I don't see the data in the folder.
Okay. So, but that
Can you
is
go
where
to search? Can you go where is the data?
it's in this folder.
In that folder.
Yes, ARA modeling 2025.
But how comes it's telling you that you cannot connect? Is you go and check in that's inside that folder because telling you cannot find the file, that means it's not there.
Okay.
Can you check the name, confirm? Because if you look at open the folder and we see.
That is here.
But that is not the folder you're. Wait a bit. But did you extract that?
Maybe I don't even know how to extract it.
But can you go and copy that file there? Go the one down. the RCBD with covariate. Can you copy that?
Let me try.
Just right click on it and you see.
I've copied it.
No. I want to, you see the thing is that, is it in a zip folder or not?
Yeah, it seems to be a zip folder.
But then you need to unzip the folder first. Because if you see here under what you open, we have drive, and they all ending .zip.
Yes.
But yesterday you were able to run this, were you?
Yes, I was.
So how did you run yesterday?
I just copied this folder and pasted it there, and it started running.
Okay, you first go to your desktop and we see. And to see.
Right, so this is my desktop.
You have got to open that. So, but can you try to double click on them and see whether you can unzip it? Okay. Can you double click on that and try to open that and see?
This RCBD.
Yes.
It's not opening. Okay.
No, I think, okay, it's opening there.
Mm-hmm.
Can you try to save that somewhere else on the desktop? Save it just outside the desktop.
A lot of?
Just the normal way you save a file. You just go and save it.
Yeah, I'm lost here. Yeah, I'm lost completely now.
No. But no, that Excel there, if you expand on that Excel file, can you save that Excel file somewhere? I mean, can you save this file somewhere else? Save it on your on the desktop. Click on the save there. Okay, what you do, you copy what is inside there. Okay. You put it on the, no, don't save it there. Look for another place to save it. Go to desktop or what? Click on the desktop or somewhere to save it. Go on this PC. Okay.
So,
okay, can you just copy the whole thing? Just copy that.
Right, I've copied.
Copy that. You open open another Excel. Just open another Excel and paste it in that and then save it as another file. Okay. Okay, yes. Can you save that file there now? Click on the save up there like you did before. Okay, save as. Save as. No. No, let's go save as. Okay. I want to save it as a CSV file. Okay, put it on a desktop. You can change that to CSV. Yeah, the CSV comma. Okay, can you put it on a desktop? Yeah, save it then. The name? No, you can go ahead and save it there. Okay, put the name there. That's enough. And save.
Okay.
Okay, can you go to your R now? Oh, no, say okay. Say yes. Or say no in that case. Just say no and you continue.
Yes, now this is my
Say no. They say I may contain features that do you want to keep the workforce? Say no. Click no. Can you click the no there? No. You see where they say Excel is telling you the.
I no longer use that window.
Okay, you can leave it for now.
Yeah, it seems I'm already out of that window.
Okay, no, that's fine.
Okay.
You can stop sharing. You get one of the what you want to do is just to create a folder, put that one in, and then you can make that folder working directory, then you can run the commands.
Okay, thank you. Thank you so much.
Okay, I think it's time we can start. You can stop sharing and I share. Okay, is everybody back? Can we continue? Today we are looking at material in day 3. The material is already in the Google Drive. So please go to the Google Drive and download all the material in day 3 and put it in a folder on your laptop or where you've been working from. So day 3 today, we are going to look at day 3. Okay. Are we together? Can I see yes in the chat? Please go to the Google link and download material. My colleague Helen can repost the Google link so that you can access the material in day 3. Okay, thank you, Helen.
Prof, I saved it with today's date. They should check today's date. Yeah.
Okay. That the folder was saved with today's date. That is 1st of October 2025.
Yes.
So please pick the material. We have only 3 minutes to go. Okay, I think we are good to go. So we are going to have a bit of theory on correlation and regression. Then after we've done with the theory, we will do the practicals. So we find that correlation is a measure of the degree of linear association between two variables. And it ranges between -1 to +1. Correlation is denoted as small r or lowercase r. We have various types of correlation. Apart from the methods themselves, we have Pearson correlation, which is used for continuous data. Then we have Spearman, which is used for rank data. Within correlation itself, we have positive correlation, negative correlation, and no correlation. Positive correlation, we have a general trend within which points range from the bottom left to the top right. While the negative correlation, points range from the top left to the bottom right. When we have no correlation, it's just a random scatter of points. So the correlation coefficient, denoted as small r, helps us to determine the strength, that is the magnitude of the relationship, and the direction. So if you have r, as we've said, it ranges from -1 to +1, and you have anything between those values, then there is correlation. For example, if your small r is equal to 0.5, some school of thought says that that is moderate correlation. And if r is greater than 0.5, then that is strong correlation. And when r is less than 0.5, then the correlation is weak. When we have +1, that indicates that you have a perfect positive correlation. And when you have -1, then that is negative correlation. The negative and positive indicates the direction of the relationship, while the magnitude shows the strength of the relationship. So for r is equal to 1, we have a perfect positive linear correlation. While when r is -1, we have a perfect negative correlation. When r is equal to 0, then we have no correlation. We can also use the scatter diagram to show us whether two variables are linearly associated. So to quantify the strength and direction, either positive or negative, of a linear relationship, we use Pearson linear correlation for continuous data. For this session, we won't do any hand calculation of correlation, but just to mention in passing, here is a formula for computing correlation. So when we construct scatter diagrams, as you can see, the topmost diagram shows that the points are close to each other and almost go through the 0, line, indicating that there is strong correlation within the data, and the magnitude is 0.98. And this is positive because the values are ranging from the bottom left to the top right. So this is very strong positive linear correlation between weight and chest girth of birds. Then when we look at the one on the left, it's a correlation between flavor and oakness. We find that the points is just a random scatter of observed value. The correlation is 0.07. It's very weak. And when we go to the third diagram, we see that the points are a bit far from each other, not as in the top graph, and the value of the correlation is 0.67. So it is strong, but not as strong as in the first diagram above it. So the scatter diagram also shows you the type of correlation that you're dealing with. It is the first descriptive statistics we do when we want to do correlation and regression. Then when we have a negative relationship, the points range from the top left corner to the bottom right. So this is negative correlation, and it is strong because the points are a bit closer to each other. Then here at the bottom, we have points a bit sparse from each other or separated from each other. It's negative 0.62. That means it is strong, but not as strong as when R is negative 0.93. And for here, when we have a random scatter of points for the bottom left graph, it shows us there is weak correlation. That's why you see it's just a random scatter of points. There is no relationship between the two variables. Now, when you conduct a correlation between two variables, it does not necessarily mean that the variable on the x-axis causes the variable on the y-axis to change. That's why we say correlation is not causation. For example, if we collect data on religion and crime, we might find that there is a positive relationship between religion and crime, but it does not necessarily mean that religion causes crime. Or if we collect information of number of women giving birth in a month from a hospital, and also number of birds around the hospital also laying eggs and hatching, you will find that there is a positive correlation, but those two variables don't cause each other to change. So when you conduct a correlation, you can only talk about the relationship being positive, strong relationship, but we can't infer that one variable causes the other to change unless if we conduct an experiment. If we conduct an experiment of fertilizer being applied to the field and the yield, then we run a correlation of yield and fertilizer quantities, and we find that it's a positive relationship, then we can infer that the more fertilizer you add, the more the yield, because now it is an experiment, you have evidence. So Pearson correlation coefficient measures strength and direction of a linear relationship, but not a causal relationship. In R, we can compute the correlation coefficient using command co in bracket. You put in the X and the Y axis variables. And if you want to test the association between pair of samples, then we use co.test. And also co.test returns both the coefficient and the p-value of the correlation. So here is a detailed commands. If you're using co, you have to specify your X and Y, then method. You have to pick whether it is Pearson, Kendall, or Spearman, depending on the type of data you have in X and Y. Then co.test, we said it brings the p-value and also the correlation coefficient. we have to indicate our X and Y variable and also choose the method. Note that X and Y are numerical vectors with the same length when you're doing the correlation. So if they are not same length, you'll find that the program is going to complain that X and Y are not of the same length. So you have to check and find out. So when it comes to a scatter diagram, we said it is a descriptive method to show us the type of relationship that we have within our variables. So we can use the package called ggplot2, and under that ggplot2 we have ggScatter command, where we highlight the file or the data file. Then we highlight or indicate the X, the Y. We can add a regression line. We can add a confidence interval. We can add correlation coefficient. We specify the method and then name the X and the Y axis. So from here, the output you get for this particular type of data, you can see the correlation R is equal to 0.92 and a p-value of 2.2 to the power minus 16. So we are testing a statement that price and weight are linearly related versus they are not linearly related. So the null hypothesis is that price and weight are not linearly related, while the alternative says that price and weight are linearly related. So when we get a p-value like this one smaller than the significance level, which we normally for sciences state as 0.05, depending on the sensitivity of the data and also level of precision. So assuming our significance level is 0.05, comparing it with this p-value, which is 2.2 to the power negative 16, this p-value is smaller than 0.05, indicating that there's evidence to reject the null and conclude that there is a strong positive correlation between price and weight, given the diagram we have in our notes. So when you use the core.test in R, you get this information below. So here ASS is the name, the object name of this command. Then core.test is the command. Diamond is the file, and we get weight. Then diamond $price is the Y variable, and the method is Pearson. So after you've run this in R, you now ask to print the object, and it gives you the information below. Under this information, we get the p-value for the test. We get the correlation coefficient. We also get the confidence interval for the correlation coefficient. So the next slide interprets the results, which we've already talked about. We've said that there is a significant positive correlation between price and weight. Okay. So sometimes you have so many variables, for example, 5 or 6, and you want to find out whether they are correlated. We normally, when you go into R, put in all the continuous variables in a file and then ask for their correlation. And you get a correlation matrix, which shows us the dependence between multiple variables at the same time. So all variables have to be numerical in the data set. In case you have categorical variables, you have to remove them, like the way Dr. Namaweje told us yesterday. The package we need to run the correlation is HEMSC package, which we can get online. It's free of charge. So before we go to linear regression, let me check in the chat in case there's any question. Any question? Day 3 registration, my colleague will post it. Dr. Helen, please post the day 3 registration if you have it, or request Reforum to post it. This is the Google link, but there is a registration form for day 3, which I saw being posted in the Google, in the chat. So maybe Reforum has, oh, it is here. Thank you, Fernando, for posting it. Okay. What do you use the confidence interval? We know that confidence interval shows us a range of possible values within which our correlation can or false. Those are the possible values of the correlation. Okay. Then we can have correlation for categorical variables. In that case, we need to code our data or rank the data and use the Kendo tau B for that. What are the packages to download? I will have the packages during the practical, but the package is called HEMSC, which we'll download, but we'll show that during the practicals. Okay, the Google link has already been shared. Let me check in queue. Oh, okay. Okay. So let's continue. Once we find that a pair of variables have significant linear correlation, then the relationship between the data values can be roughly approximated by a linear equation. Now, the process of finding the linear equation that suits our data is called linear regression. And the line of best fit is called a regression line. So linear regression is a relationship between variables, and the objective of the regression is to identify the relationship, either it's linear or nonlinear or curvilinear, then estimating the parameters, the slope and intercept, and also prediction is one of the objectives of regression. After you've estimated the slope and intercept, we use that equation to predict the response for any given value of the independent variable. We can also validate the relationship, as we shall see, using the residual plots. The linear relationship is a straight line, which consists of y being the response, b0 is the intercept, and b1 is the slope, while x is the independent variable. Now, why do we call it a response? We call it a response after you've performed an experiment. For example, if we measure different quantities of fertilizer, apply it to the plots, then we plant corn. After it has grown to a certain level, we measure maybe the height, number of leaves being produced, then eventually we measure the yield. The yield is responding to the quantities of fertilizer you're applying to the plots. So the yield has variability and responds to any change in x. Meanwhile, x is measured with minimal error. So that's why we call x independent, while y is the response or dependent variable. B1 is the slope of the line, and we define B1 as the value of y when we increase for every increment in the independent variable x. So if for every unit increment in x, y changes by B1. Meanwhile, the intercept is the value of y when x is equal to 0. For us to estimate the slope and intercept, we use a method called ordinary least squares regression, or ordinary squares. In ordinary squares, we try to minimize the difference between the observed response and the fitted line after regression. But we'll see later that when you fit a line onto your data, not all values fall on that line. And the difference between the observed values and the fitted line is what we call residual or error due to other factors. So the line that we fit onto our data, called the line of best fit, minimizes the squared terms or error terms that are obtained by least squares method. And the slope and intercept obtained by least ordinary squares are called least squares estimates. So we see in this plot, the red dots are the observed values that you collect from the field, and the blue line is the regression line, which has been superimposed onto the red. We see that the red points do not actually touch the blue line, not all of them touch the blue line, and the difference between the red point and this line here is called the residual. So the regression line is represented as y hat, hat meaning estimated, is equal to the slope b1 x plus b naught. Why is the slope positive? Because the trend is positive. If we had a negative trend, our slope would be minus b1. So we've said that because not all points touch the blue line, whatever remains, the difference between the observed and the predicted is equal to residue. Now, the predicted values are those values, if we go back to our plot, this equation here, once we have the value of the slope and intercept, for any value of x, we can predict y. So if for your data set, if you predict y for all the given values of x, we can now get the difference between the predicted and observed value, and that difference is what we call residue. So here is an expanded form of what we are talking about. So this is the red points, observed data. We fit a model line, which is the regression line. And when we expound this, we find that there is a difference between the blue line and some red points. And that difference is what we call residue. The model line gives us the predicted value, y hat, and the red points are the observed. So that difference between y and y hat is residue. So the ordinary squares regression minimizes the sum of the square differences between observed and predicted values. And when we sum up those residuals and square them and differentiate with respect to the slope and intercept, we are able to now come up with the equations for estimating the slope and intercept. So from this, we can see that the intercept has a formula, which I For now, I do not want you to cram, but it's always good to know what the computer is giving you. So beta naught is equal to y bar, the mean of the response, minus the slope into the mean of the independent variable. Meanwhile, the slope is the cross product of x and y over the sums of squares for x. So they've been expanded down here. We can see the cross product of deviations for x from the mean and the deviations from the y means. When we multiply these deviations and sum them up, we get the sum of cross product for y and x. Then the sums of squares for x are the deviations of x values minus the mean squared. Meanwhile, the mean, we know that when we sum up all the values of x and divide by total number of observation, we get the mean. The same applies to y. We can also estimate the parameters using this formula here. This is expanded format. And then we can also get formulas for the residual, etc. So the residuals are deviations of observed and predicted value, as we said. But when we run a regression, we get what we call error or residual sums of squares, which is a sum of the square deviations of observed minus the predicted values. And when we divide the sums of squares by degrees of freedom, we get an estimate of the variance of the data, which is sigma hat squared. When we get a ratio of the sums of squares and total variation in the response, -1, gives us the coefficient of determination. Coefficient of determination tells us the percentage of variability explained in the response after running the regression model. So R squared is the coefficient of determination. It tells us the proportion of variation independent or response variable that has been explained by the regression model. So if we have 3 or 4 models to compare, we can look at the R squared, and the model with the highest R squared gives us a better fit to the data. But if the model has more than one independent variable, we normally prefer to use R squared adjust because it adjusts for any parameter added in the model. So if we start with a model with intercept and add in a variable x1, R squared adjust is going to adjust for adding x1 because you've added another slope. However, R squared only just increases. So when we are dealing with model building, we look at R squared adjust because of adjusting for any parameter added in the model. In the linear regression model, we test for the assumption, or we test for a statement that there is no linear relationship between the response and the independent variable, and statistically it is denoted as H0 as the null hypothesis, B1 being the slope is equal to 0. So if the slope is equal to 0, we'll have a straight line relationship. And that relationship looks like this. So we'll have something like this when there's no slope. So this is y and this is x. So if there is a relationship, meaning B1 is not equal to 0, then our relationship could either be like this or be negative, depending on the value of the slope. We can test this hypothesis using either t-test or an analysis of variance table, as we shall see later. Now, the t-test has a formula here. which is B1 minus 0 over the standard deviation of the data over the square root of sums of squares, which we've already defined. And this t-test corresponds to degrees of freedom n minus 2. N minus 2, we get it from the analysis of variance table. It corresponds to the degrees of freedom for residue. Where do we get the 2? In our model, which is the simple linear model, because we only have one independent variable, therefore it's called the simple linear model. This model here. We have two parameters, the intercept and the slope. That's why here we have the degrees of freedom n minus 2. We shall see later the details of degrees of freedom. Any questions so far? Okay, I'll go in the chat. T-test is normally when the data follows a normal distribution. And one of the assumptions under regression is that the data has to be normally distributed. We will look at that. Is the intercept a parameter? Yes, we have two parameters, population parameters, the intercept and the slope. Data registration, I think forum will send. Which R squared when we are dealing with the comparing different models with more than one independent variable, it is preferably better to use R squared adjust, because as you add in more variables to the model, it adjusts for any other parameter added into the model. Okay. 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 Okay, so if there are no more questions, we can go ahead.
Prof, there is a question in the Q&A.
Apparently, I can't access my Q&A.
Ah.
I don't know where it disappeared. Let me check it down here. Can you read the question for me, Helen?
Yes. Eric is asking that what is the acceptable level of correlation between covariates to run a regression?
Okay, thank you. If the correlation is greater than 0.5, then we can run a regression, because that shows that there is a strong relationship between the two variables. It depends on what statistical book you're reading. Different statistical books have different ranges. So normally when you're interpreting your data, look at any statistical book and use it as a reference. Okay. So, but the one I use has greater than 0.05 is strong, less than 0.5 is weak, and R is equal to 0.5 is moderate, R is equal to 0 is no correlation. So when R is greater than 0.5, then there is a strong relationship between the response and independent variable. We also know that one thing that I had skipped is that the correlation coefficient, small r, is related to R squared adjust, or R squared. So if we square correlation, we get R squared or R squared adjust. Okay, so if we go back to our notes, we will, when we are doing practical, we'll find out. that when you get a correlation coefficient and square it and look at the R squared, you find that it is similar. So if your R squared is greater than 0.5, then when you run your regression, even R squared is going to be higher. Okay. So we say that we can test our hypothesis using a t-test or an analysis of variance table. The analysis of variance table separates the total variation in the response into regression sums of squares and residual sums of squares. So the total sums of squares is denoted as SYY, regression sums of squares, we denote it as SR, and then the residual is SE. So if we add regression and residual, we get the total sums of squares. And if we get a ratio of sums of squares, R, regression sums of squares over total sums of squares, gives us the R squared. So this is an output from a software, and the analysis was between volume and diameter. So when you perform an analysis of variance table, the first thing you look at is the degrees of freedom to ascertain whether that analysis is correct. Because in case you enter anything wrong, then it's going to come up in the degrees of freedom. If you have more values than what you should have, in the degrees of freedom, you will have also more values. So the regression degrees of freedom is equal to the number of parameters minus 1. So in this model here, we have volume, the intercept, and the slope. So we have only 2 parameters. So in that case, the degrees of freedom will be P minus 1. So number of parameters minus 1 gives us degrees of freedom for regression or the number of independent variables in the model. So if we look at this model, we have 1 independent variable. Even here, we have 1 degree of freedom. Number of parameters are 2. 2 minus 1 gives us 1 degree of freedom. When we come to residual error, the degrees of freedom is n minus p. N minus p, where p is the number of parameters in the model. Now here, the total degrees of freedom is equal to n minus 1. That tells us that the total n number of observation will be 31. This one, we just add 1 on this side and also add 1 on this side. So giving us n is equal to 31. So our residual will be 31 minus 2 parameters in the model gives us 29. So once your degrees of freedom here are okay, then the rest of the output is going to be correct. Sums of squares, there is a formula which we won't talk about now. Mean square is the ratio of sums of squares. So here we have sums of square regression over degrees of freedom for regression. That gives us our mean square for regression. Mean square for error or residual is going to be sums of square error over degrees of freedom for error. Then the F ratio is a ratio of mean square regression and mean square error. So the F ratio ends up with 2 degrees of freedom. The numerator corresponding to the residual and the denominator. So the F has V1 and comma V2 degrees of freedom, where V1 is the numerator and V2 is the denominator. The denominator corresponds to the error mean square, where the numerator corresponds to the regression mean square. So with the F value, if the F value calculated, the one in the table you see, which is 4.400.36 is greater than the one you get from the table, F tables. You will go in your free time and look for the F distribution tables. Then we have evidence to reject the null, which null was saying that there is no linear relationship between volume and diameter. We can also use the p-value to make interpretation. So our p-value is 0.000. And remember, our significance level is 0.05. Now, the significance level is the probability for the null assumed to be correct. So we assume that the null is correct at a chance of 5%. Anything below 5%, we have evidence to reject the null and conclude that there is a significant relationship, linear relationship between volume and diameter. So in this case, since our p-value is less than 0.05, we have evidence to reject the null. Remember, the null was saying that there is no linear relationship. The null says that no slope, beta 1 is equal to 0, meaning no linear relationship between volume and diameter. And since we have evidence to reject this, we conclude that there is a significant linear relationship between volume and diameter. Then we also look at the R squared. It's 93.5%. We are going to say that the amount of variability explained in volume by the regression model is 93.5%. So most of the variability has been explained in volume. If our R squared was less than 70%, then that model is not a good fit for our data. We need to look for other factors to explain the remaining 30% or more. We also have our R squared at just here. It's the same interpretation. The amount of variability explained in volume by the regression model is 93.3%. Now we see 18.1 is the mean square error. If we get a square root of this, we will get the standard deviation of the data. Any question about the interpretation in the chat? Any question? If the P is greater than 0.05, we have no evidence to reject the null. We conclude there is no linear relationship, significant linear relationship between volume and diameter. So if our P for the null to be assumed to be correct is 0.05, anything greater gives it higher chance to be correct. So we have no evidence to reject the null when our calculated p-value is greater. I do not understand the F value. Okay. Please explain P and N in the analysis of variance table. Okay. Okay, let me explain that. The F value, I'm going to go off. I'm going to stop sharing and get an F table from Google. F distribution. Okay. I'm sharing the F distribution table. So the F distribution table looks like this. It's a statistical table. Every statistical book has F distribution. We have D1, which is the numerator degrees of freedom, and D2 is the numerator degrees of freedom. So remember, in our analysis, our numerator or regression degrees of freedom is 1, and denominator is 29. So I don't know whether it goes up to 29. Let me get one which goes up to 29. Stop sharing. Okay, let's share this one. Okay, so we find that our DF numerator degrees of freedom is 1 and denominator degrees of freedom is 29. So the value intersecting 1 and 29 is 4.81. So that is the tabulated F value. So let's go back. I'm going to stop sharing and share the notes. Okay. So somebody was saying doesn't understand how F is interpreted. Now we remember that what we've gotten from our statistical table, F from the table at 5% is 4.18. Now, when the calculated F value is greater than the tabulated F value, we have evidence to reject the null. Or we can even put it on a plot. The F table is not symmetric. So our critical value would be here, 4.18. And this is the rejection region. If you are to mark off 400, it's going to be in the rejection region. 419 is going to be in the rejection region. So you have evidence to reject the null. Then somebody that says they don't understand N. Now, the total degrees of freedom is equal to N minus 1. So if we have total degrees of freedom at 30, so we are going to have 30 is equal to what we don't know, N minus 1. Then add 1 on this side. Whatever you do on one side, you do it on this side. Minus 1 plus 1 becomes 0, and 1 plus 30 is equal to 31. So the total number of observation is 31. Okay. Any other question in the chat? Please, I need YouTube record. Okay, Can you repeat interpretation if possible? That's what I've been doing. Let me see any other question. Okay. Okay, if there's no any other question, let's wrap off and continue. Okay. So in your free time, there is an exercise here you can work out. It's about amount of inorganic phosphorus retained in soil, and there is a data set there. So let's look at the assumptions under linear regression. We assume that the response is a random variable, normally distributed with mean mu and variance sigma squared. We assume that the random errors or residuals are assumed to be independent, meaning they are not correlated, normally distributed with mean 0 and constant variance. Here we should have constant variance sigma. So how do we test those assumptions? We use the residuals. We know that residuals are obtained by subtracting the observed data and the fitted values. Now, the residual plots, just like my colleague explained this afternoon, we use them to test those assumptions under the simple linear regression. Simple linear regression is when we have one response and one independent variable. For the response to be linear related to x, which is the independent variable, just construct a scatter diagram. If you observe a linear relationship, then we are good to go. For normality, we can use a QQ plot, which we shall see in the oral histogram of residues. Okay. So when a model is correct, the residuals are assumed to be normally distributed with constant variance and no correlation. A histogram of residual is used to check normality of residuals. Or we can also use the normal probability plot, which is a plot of residuals versus normal score. We can test the assumption of constant variance and randomness using a plot of residuals versus fitted value. For example, here we have a plot showing constant variance. It's a plot of residuals versus fit. So long as there's a random scatter of points, no pattern in the points, then we conclude that the assumption of constant variance is not violated. Now, anything that deviates from this, we have to pay attention. For example, if we get a plot like this one, if we get a plot, we have our residuals here. That is the mean, which is 0 of residuals. And we get residuals forming a band like this, a bow-shaped. So I'll like that. Meanwhile, this is fitted value. It is showing us that the residuals are increasing as the fitted value increase, as well as decrease as the fitted value decrease. Here, it's likely that our response has two outcomes, positive and negative, and we can eliminate this by running a logistic regression, taking into account the binary nature of the response. Or we can use natural logarithm of y and x, and then rerun the regression to correct this problem. The bow-shaped here shows us that the variance is not constant, and it is also showing us that the response has a binary nature. Then what if you get something like this, residuals, fitted, and you have a curvature, a curve. So if you get a curve like this, it shows you that, first of all, the residuals are increasing with fitted values, indicating non-constant variance, but also it is showing us that the linear model doesn't actually fit our data, since we are getting a curvature, and it's telling us that we should model our data using either a quadratic or a cubic, depending on what is going to be visible. If we get something like this, a funnel-shaped, if we get a funnel-shaped like that, we have our residuals here, and we have our fitted values here. This shows us that the residuals are increasing with increasing fitted value, also decreasing with decreasing fitted value, showing non-constant variance, and we can use natural logarithm to stabilize this problem. Okay. Let me go ahead with, so I'll rub off this. Let's look at other plots. Independence. If we have a plot of residuals versus time order, for example, if we have something like, this is our residuals, and then our fitted values, then we have a time series graph showing that we have peaks and troughs in your data. It implies that the residuals are correlated, and we should run a time series, something like that. So residuals have a time series nature in them. You can either run time series analysis, or you can use natural logarithm to remove this, or you can use mixed model to take into account this correlation. So for you to see no correlations, this should be just a random scatter of points, no pattern in the graph. Okay. Then for normality, we said we use histogram of residuals or the QQ plot. So if the histogram shows a bell-shaped graph, then we know that the residuals are normally distributed. For the QQ plot or normal probability plot, the residuals should fall in the line, like fall on the line that goes through the data. So we have residuals here, and we have normal score down here. So then we have a line in the middle. Our values should fall on this line to show us that there is normality in the residuals. So in case you get the residuals deviating from this line like this, or going up like this, or even coming down here or up, then the residuals are not normally distributed. So we can use still natural logarithm to remove non-normal residuals. Okay. So we talked of applying the quadratic and cubic to the X variable to model the curvature in case the residuals show you a curve. And that type of regression is called polynomial regression. Tomorrow, we will go through practicals, and we are going to see how a polynomial regression looks like, and how the residual plots appear when you, instead of using polynomial regression, you just use a linear regression. Now, sometimes we find that the linear relationship between the response and independent variable, the R squared that we get is so small, and it indicates that there is a lot of variability unexplained in the response. So in that case, we need more predictors to be added into our model And when we have a model where we have one response and many independent variables, that type of regression is called multiple regression. And the linear relationship appears like that. We have the response here, the slope, the intercept, slope for x1, slope for x2, and then epsilon. We can have more than 2 independent variables. So in that case, this is no longer simple linear. It is called multiple linear regression. Now, the assumptions under simple linear also hold for multiple linear regression. We will assume y is a random variable, linear related to all the x's. We also assume it is normally distributed. We also assume the random errors are normally distributed, independent with constant variance. And another added assumption is that we assume the independent variables are not correlated under multiple regression. So this is an analysis out of multiple regression. And the most important thing here is how do we interpret this regression line or equation. So with multiple regression, you hold one independent variable constant and interpret the other. For example, we can hold height constant and interpret diameter. So if we are interpreting diameter, for every unit increment in diameter, volume increases by 4.71. We are saying increase because it is a positive relationship. If there was negative here, for every unit increment in diameter, volume would be decreasing by 4.71. But in this case, it is positive. Therefore, volume increases by 4.71 for every unit increment in diameter. Then we hold diameter constant and interpret height. For every unit increment in height, volume increases by 0.339. The intercept is the value of volume when diameter is equal to 0 and height is also equal to 0. So in this output, we see the coefficients corresponding to these values we've been interpreting, and thus the standard deviation, the t-value, and the p-value. So how do we get this t-value? We get the coefficient divided by the standard error of each coefficient gives us the t-value. And we have the corresponding p-value, and it is testing the hypothesis that there is no linear relationship between volume and diameter, and also no linear relationship between volume and height. But we see that all these p-values are less than 0.05, so we have evidence to reject the null and conclude that there is a significant linear relationship between volume and diameter, as well as a significant linear relationship between volume and height. Even here we get our R squared, but in this case we use R squared adjust because when we add height into this model, R squared adjusts for this extra parameter added. So this implies that the amount of variability explained in volume by the regression model is 94.4%. This is the analysis of variance table, which comes with that type of analysis. And as we interpreted in the simple linear, even here, the F value, we go in the table, get a value corresponding to 2 and 28, or we use the p-value. Since our p-value is less than 0.05, we reject the null and conclude that overall, there is a significant linear relationship between volume, diameter, and height. Down here, we have sequential sums of squares indicating the contribution of each independent variable to the regression sums of squares. So we see diameter contributing a lot compared to height. So it shows contribution of the amount of explained by each independent variable as far as the regression sums of squares is concerned. Okay. So again, if you want to practice overnight with R, you can input this data and interpret. So we have 9 minutes left. Let's just look at indicator variables and then call it a day. Sometimes we've been dealing with continuous independent variables, but sometimes you get data which is categorical. And categorical data has groups. For example, if we have a variable, assuming we have volume, diameter, we have height, and then we have species. So under species, we have species 1, we have species 0. Let's say there are 2 groups only. So we want to find out whether we can fit one regression line onto species 1 and 0, or we can fit separate lines, or we can fit parallel lines. So in that case, we create a new variable to represent our species. Remember, these species, this can be, I think you've heard of the eucalyptus clone. One can be called a GU, another an GC. Okay? So if we want to predict the volume for GU and GC, can we use one regression equation? Or we need parallel regression equation? Or we need 2 separate regression equations? So by giving codes to GU and GC, we are able to model our data. So already here I've represented them as codes 1 and 0. They do not have any meaning. It's just a numerical way of representing the categorical information. Now, the number of variables to include in our data set depends on the levels of the categorical variable. How many groups does the categorical variable have? If we had another maybe grandis here, let's represent it as G. So we are saying that if species is GU, then we code it 1. If species is GC, we code it 0. If species is G grandis, we can call it 2. Can call it 2. Or we can call it 1, depending on how we are designing our dummy variables. So we create what we call indicator variables or dummy variables for this categorical variable. If there are 2, we need only 1 categorical variable. We get the number of categories minus 1 is equal to 1 variable that we need to create. If there are 3, we create 2, because 3 minus 1 gives us 2 variables that we are going to create to represent our dummy variable or indicator variable species. Any questions so far? Okay. We have 6 minutes left, and I think I'm going to stop there. I don't know if we are still fresh. We can continue. I have no problem continuing with more information. But in case people feel like there's a lot of information given and they are circulated, we can call it a day. What, should we continue? Can I see in the chat? Should we continue? Okay, they say we continue. Okay. I've seen 1 no, 2, 3, 4, 5, 6, 7. Others are saying we continue. Others are saying no, tomorrow. Yes, yes. Call it a day. No, 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 no. Okay. I think let's call it a day. I can see a lot of no compared to the yes and tomorrow. So we'll continue from here tomorrow and also do practicals tomorrow. Okay, same time 2 to 5. Okay, thank you very much. I hand over to my colleague, Thomas. He's the one who started the session today. So see you tomorrow. Thank you for attending the session. Okay, Thomas, are you still here? Oh, Helen? Oh, I hand over to Reform. Okay. Okay. Okay, I think Reform.
Okay, Prof, thank you very much.
Okay.
Thank you very much, Prof, for the good lessons. Once again, we want to thank the participants for being here with us up to now. We want to thank you so much for acknowledging the importance of these trainings, and please let us see you again tomorrow. I see many of you are asking for the link of YouTube, the YouTube link. Please do visit the Reform Network YouTube channel on YouTube. You'll find all the recordings for day 1 up to today. So we have tried to post the link for the session today, but we still see a lot of you asking for the link. Please do get on our YouTube channel, subscribe, and you will have access to all those trainings whenever they are happening, and at any time, actually, even after the training session. So thank you very much. We look forward to seeing you tomorrow, and thank you very much, Professor and the team.
You're welcome. Thank you too.
Okay, bye-bye.
Okay, bye. See you tomorrow, same time.